Forget everything they taught you. Let's go. Number 10. Magnetic field alignment. When Voyager 1 crossed the heliopause in August 2012, the magnetometer team at NASA Goddard expected a dramatic shift. The galactic magnetic field, the one that fills the space between stars, should have pointed in a completely different direction from the Sun's field. That's what decades of modeling predicted. A sharp twist, a clean break. That's not what happened. Leonard Berlanga and his team stared at the data and saw something nobody anticipated. The magnetic field outside the bubble pointed almost the same way as the field inside. Voyager 2 crossed 6 years later, in a different location, at a different point in the solar cycle, and got the same result. 2 probes, 2 different paths, same bizarre alignment. Here's why that's a problem. If the fields line up, they can connect. And if they connect, charged particles from the galaxy can slip into our solar system along those connected field lines, like cars merging onto a highway. It works both ways. Solar particles leak out, too. The heliosphere, the sun's protective magnetic bubble, suddenly looks a lot leakier than anyone thought. One explanation is that past supernova explosions shaped the local interstellar cloud and forced its magnetic field into a direction that happens to match ours. Pure coincidence of galactic geography, but there's a more unsettling possibility. The fields actively reconnect and weave together at the boundary, forming tubes that link inside and out. Permanent open doors in a wall we assumed was solid. Neither explanation is fully confirmed. And that matters because the direction of a magnetic field controls where radiation goes. If our shield has open lanes, the edge of the solar system isn't really an edge at all. But the magnetic field wasn't the only thing behaving strangely out there. Number 9. Solar wind reversal. The sun blows a constant stream of charged particles outward at roughly 1,000,000 miles per hour. That stream, the solar wind, is what carves the heliosphere in the first place. It's supposed to push outward, always outward. That's its entire job. But far from the planets, Voyager found something that broke that assumption. The wind doesn't just slow down out there, it stalls. And sometimes, this is the part that surprised everyone, it actually pushes back toward the sun. Voyager 2 had a working plasma detector, an instrument Voyager 1 had lost years earlier. John Richardson's team at MIT watched the readings come in and saw particle speeds collapse from hundreds of kilometers per second to nearly zero. Then, at times, the flow turned sunward. Picture a river hitting an incoming ocean tide. The fresh water doesn't just stop. It sloshes, it churns, it gets shoved upstream. That's happening at the edge of our solar system. The interstellar medium presses on the heliosphere, and when the sun goes quiet during its 11-year cycle, the outward pressure drops and the boundary actually moves inward. What surprised the modeling teams wasn't the slowdown itself. They'd predicted some version of that. It was the messiness. The reversals weren't smooth. They came in fits and surges, as if the boundary were breathing. Whether that breathing is steady or driven by individual solar storms is still debated. What isn't debated is the consequence. The radiation environment out there doesn't sit still. It pulses, and the next discovery showed just how violent that pulsing can get. Number 8. Wall of fire. Step past the sun's protective bubble and the temperature reading jumps to somewhere between 30,000 and 50,000 Kelvin. For reference, the surface of the sun is about 5,800 Kelvin, so the space just beyond our solar system is, by this measure, hotter than the surface of the star that made it. Now, it won't burn you. There's almost nothing out there. The particles are so sparse that a probe flies through without damage, but each individual particle is moving absurdly fast, and when physicists measure particle speed, they report it as temperature. Don Garnett's team at the University of Iowa ran Voyager's plasma wave instrument, a sensor that listens to faint oscillations in the surrounding plasma and converts those tones into density and temperature readings. What came back was a spike that no model had predicted with any confidence. A compressed layer of superheated plasma sitting right at the boundary, registering tens of thousands of Kelvin. 2 processes probably create it. The first is compression. The interstellar medium pushing against the heliosphere squashes the outgoing solar wind plasma until individual particles accelerate under pressure. Same principle as air heating up when you pump a bicycle tire. The second is magnetic reconnection. Tangled field lines snapping apart and flinging their stored energy into nearby particles like an invisible slingshot. Together they produce a thin, superheated shell wrapped around the entire heliosphere. It's sparse enough that probes survive, but the energy it carries feeds everything that comes next, including the cosmic ray surge waiting just beyond. Scientists had to scrap models that showed a gentle, gradual transition into cold interstellar space. There's nothing gentle about it. Number 7. Cosmic ray spike. Inside the heliosphere, the sun's magnetic field does something critically important that most people never think about. It deflects a huge fraction of the galaxy's most dangerous radiation. Galactic cosmic rays, high-energy particles moving close to the speed of light, slam into our magnetic bubble, and most of them bounce off or slow down before reaching Earth. When Voyager crossed the heliopause, that shield vanished. The low-energy charged particle detector, managed by Stamaeos Krimigas and his team at Johns Hopkins Applied Physics Lab, recorded a sudden threefold jump in galactic cosmic ray intensity. At the same time, the solar particles that had been riding inside the heliosphere dropped to nearly zero. That crossover confirmed something theorists had predicted for decades. The heliosphere genuinely protects the inner solar system from galactic radiation, but the data also revealed something they hadn't predicted at all. The cosmic rays didn't rise smoothly, they climbed in steps. In some energy bands, the increase was sharp and sudden. In others, it arrived from particular directions rather than spreading evenly. If the heliopause were a simple barrier, you'd expect an even flood the moment you crossed it. That's not what the instrument saw. The step structure suggests two things happening simultaneously. Shocks and turbulence right at the boundary are boosting particle energies locally, a kind of secondary acceleration happening in the transition zone itself. And magnetic field lines that connect across the boundary are channeling particles along specific lanes, creating directional beams instead of a uniform wash. The practical problem is real. Radiation beyond the heliosphere isn't a smooth, predictable background you can just average and engineer for. It's patchy. It's directional. It comes in spikes. Any spacecraft or crew venturing past the bubble needs shielding designed for the worst moments, not the average. And the particles weren't the only thing piling up at the edge. Number 6. Plasma density jump. Just past the heliopause, the number of electrons and ions in the surrounding plasma jumps by somewhere between 10 and 50 times what it was inside. That's not a typo, 10 to 50 times. Voyager 1 caught it first, indirectly. The plasma wave instrument measured oscillation frequencies that spiked upward, and from those frequencies scientists calculated a massive density increase. Then Voyager 2 crossed with its working plasma sensor, the one Voyager 1 had lost, and confirmed it directly. Think of it this way. The solar wind flows outward for billions of miles, getting thinner and thinner the whole way. Then it hits the interstellar medium, a cold, comparatively dense wall of material that isn't going anywhere. Particles compress at the border like traffic backing up at a toll booth. Three things cause the pileup. Compression from outside pressure. That's the most straightforward, just the interstellar medium leaning in. Charge exchange, where fast solar wind ions swap electrons with slow interstellar neutrals, creating a whole population of sluggish new particles that clog the flow. And reflected shocks, pressure waves from solar eruptions that travel out, hit the boundary and bounce back, trapping plasma temporarily. What's telling is that the jump isn't the same everywhere. It varies depending on where you cross, when you cross, and what the sun's been doing recently. Some readings showed a 10-fold increase, others showed 50. That range alone tells you the heliopause isn't one consistent thing. It's layered and dynamic, and its character changes with time. There's a practical angle most people miss too. Plasma density controls how radio signals travel. Communications with a future interstellar probe won't behave the way they do inside the solar system. The density jump changes the rules. But what was happening to the magnetic field itself was even stranger. Number 5. Magnetic and plasma anomaly. This is where Voyager's instruments started picking up things nobody could quite explain. The magnetometer recorded sudden twists in field direction, tight corkscrews and flat reversals that appeared and vanished over the span of hours. The plasma wave receiver picked up bursts and hums that sounded, when converted to audio, like a stormy sea. What the instruments were seeing was foam, magnetic foam. Imagine ocean waves hitting a rocky jetty. The smooth surface breaks into froth, spray, and pockets of trapped air that swirl and collapse. The heliopause does the same thing, except with magnetic fields and ionized gas. Field lines from the sun and field lines from the galaxy collide at the boundary, break apart through reconnection, and form isolated bubbles of trapped plasma. Physicists call these magnetic islands. On top of that, shear-driven instabilities create vortices wherever flows slide past each other. Solar eruption shocks crash in from behind and churn the whole mess further. Charge exchange with neutral atoms adds another layer of complexity. Voyager 1 and Voyager 2 crossed in different places, years apart, and got different snapshots. Sometimes sharp, clean boundaries, sometimes gradual froth. That variability is actually the finding. The heliopause isn't one thing. It's dozens of overlapping processes creating a shifting, leaky patchwork. Particles don't need to punch through it. They ride the bubbles and slip through gaps in the field. The barrier exists, but it's riddled with side doors. And on the other side of that foam, there's a region that earned a genuinely haunting name. Number 4. Cosmic Purgatory. Before Voyager 1 officially entered interstellar space in August 2012, it spent nearly a year stuck in a region that the team at JPL started calling the Stagnation Zone. Ed Stone, who'd been Voyager's project scientist since before the 1977 launch, described it to reporters as a kind of cosmic purgatory. The name stuck because it fit. In this zone, the solar wind drops to a crawl, practically dead still. The magnetic field strength roughly doubles as field lines pile up like cars in a parking lot that's full. And something unsettling happens to the particles. Solar particles plummet while high-energy electrons from outside the heliosphere surge by about 100-fold. It's a logjam. The solar wind keeps arriving, but it can't push through. Interstellar pressure holds the line. Meanwhile, reflected shocks from coronal mass ejections, the sun's biggest eruptions, hammer into the congestion from behind, bounce back inward, and stir particles into magnetic pockets. The stagnation zone persists for months, sometimes longer. It's not a line you step across, it's a region you crawl through, and while you're in it, the radiation environment becomes genuinely chaotic. Particle flows arrive in bursts from specific directions, not as any kind of steady background. And what troubled the science team wasn't just that the zone existed. Some compression was expected. It was how structured and stubborn it was. This wasn't a thin transition layer. It was a place with its own internal weather, its own cycles. Voyager spent far more time negotiating it than the models had predicted. The boundary was fighting back, and when scientists looked at the big picture of what Voyager had mapped, the shape it revealed was nothing like the textbooks. Number 3, the shape of the heliosphere. Here's what textbooks used to show. A neat, comet-shaped bubble with a smooth nose and a long tail trailing behind the sun as it moves through the galaxy. Clean, symmetric, elegant. Voyager destroyed that picture. Voyager 1 hit the termination shock, the inner boundary where the solar wind first slows from supersonic to subsonic, at 94 astronomical units from the sun. Voyager 2 hit the same boundary at 84 astronomical units. That's a 10 astronomical unit difference, roughly 1.5 billion kilometers. Since the two probes crossed in different directions, that gap proves the heliosphere isn't round, it's dented. The interstellar magnetic field pushes harder on one side, squeezing the southern hemisphere inward. Beyond the raw distance, Voyager's magnetometers recorded magnetic bubbles, oblique ripples, and layered density ramps that shift with the sun's 11-year activity cycle. The heliopause breathes. It expands when the sun is active and contracts when it's quiet. Solar eruptions smash into it and send reflected waves back inward. Reconnection events tug field lines into flux tubes that bridge the inside and outside. The latest simulations, built on Voyager's real data instead of guesses, don't show a comet shape anymore. They show something closer to a deflated croissant. 2 lobes, no clean tail. Some models still argue about the tail. What every model agrees on is that the old symmetric picture is dead. The consequence is straightforward. If the bubble's shape is uneven, then the shielding it provides is uneven. Radiation levels and particle flows outside the heliosphere depend on direction, time, and what the sun's been doing recently. It's not a fence around the solar system. It's a weather pattern. And speaking of sounds nobody expected from the void. Number 2, the interstellar hum. Space isn't silent. Voyager 1 proved it. After crossing the heliopause, the plasma wave instrument, the same sensor Don Gurnett's team used to detect the wall of fire, picked up something nobody was expecting. A faint, steady, narrow-frequency tone that didn't stop. Not a burst triggered by a solar eruption. Not instrument noise. A hum. Stella Koch-Acker, a doctoral student at Cornell, led the analysis. Her team went through 4 years of Voyager 1 data and published the finding in Nature Astronomy in 2021. What they found was a persistent signal sitting quietly between the louder plasma oscillation events, the shock waves triggered by solar eruptions. If those shock waves were claps of thunder, this hum was the steady drizzle between storms. Before this, scientists could only measure interstellar plasma density during those rare shock events. Between them, there was nothing. Silence. The hum changed that. It gave researchers a continuous reading of the medium Voyager was traveling through, like picking up the background tone of an air conditioner in a room you've never entered. Suddenly, they could monitor conditions in interstellar space in real time, not just during dramatic events. So what's producing it? That's the part that's still open. Two hypotheses exist, and neither perfectly fits. One says the interstellar plasma naturally vibrates at a frequency set by its density and temperature, thermal oscillations the antenna simply overhears. The other points to quasi-thermal noise, random electromagnetic flickers caused by charged particles drifting past the instrument. The problem is the signal's too narrow, too steady, too persistent for either explanation to fully account for. There are good arguments on both sides, but no confirmation. And until another probe reaches interstellar space and either hears the same hum or doesn't, the question stays open. Voyager detected something real, we just don't know what makes it. And now, the one that broke the textbooks entirely. Number 1. The anomalous cosmic ray paradox. For 30 years, heliophysicists had a clean, confident prediction. Interstellar neutral atoms drift into the solar system, get ionized by sunlight, ride the solar wind outward, and slam into the termination shock, that inner boundary where the wind goes subsonic. At the shock, they'd be accelerated to cosmic ray energies through a well-understood process called diffusive shock acceleration. The termination shock was supposed to be the particle cannon of the outer solar system. That was the theory. Elegant. Tested. Accepted. When Voyager 1 crossed that shock in December 2004 at 94 astronomical units, the team expected a sharp peak in energetic particle intensity right there. The source. The confirmation of 3 decades of work. It wasn't there. Voyager 2 crossed in August 2007 at 84 astronomical units, 10 astronomical units closer to the Sun, different location, different solar conditions. Same result. No peak. Lower energy particles did spike at the crossing, which was encouraging, but the high-energy anomalous cosmic rays, the ones the theory specifically predicted, kept climbing as both probes moved deeper into the heliosheath, as if the source were somewhere else entirely. That single observation shattered a foundational prediction. Scientists formally call it the Voyager paradox. Dave McComas and Nathan Schwadron at the Southwest Research Institute proposed what's become the leading response. The termination shock isn't round. It's blunt and asymmetric because the solar system plows through the interstellar medium. Efficient acceleration doesn't happen at the nose, where both Voyagers crossed. It happens on the flanks, the sides, far from where any spacecraft has ever been. But that's just one possibility. Others point to turbulence throughout the heliosheath slowly pumping particles to high energy over enormous distances. Others say magnetic reconnection near the heliopause flings particles to extreme speeds in sudden bursts. Still others invoke magnetic islands, trapped plasma bubbles that accelerate particles as they merge together. Each idea explains part of the data. None explains all of it. The Voyager paradox remains one of the biggest open questions in heliospheric physics. We sent 2 probes to the edge of the solar system expecting to find answers. Both came back with a bigger question. That's the thing about the edge. The deeper you look, the stranger it gets.